Now we are going to begin talking about continuous functions from a metric space to a metric space. You may recall section 1.7 was all about continuous functions from the real numbers or a subset of the real numbers into the real numbers. So we're going to write a definition that looks exactly like the definition of continuity in section 1.7, and then we'll write down a proposition that's exactly like theorem 1.7.5. So the setup is a little different. We let xd and z comma rho be two metric spaces. A is a point in our first metric space, and f is a function whose domain is our first metric space and whose range is the second metric space. Then we say that f is continuous at A if, whenever you have a sequence of points in X that converges to the point you care about, we have that the image of the sequence also converges, and it converges to what you think it should be. And if you look, this is exactly like definition 1.7.1. And then there is an important theorem in section 1.7.5 that generalizes in a straightforward fashion to metric spaces. So we all saw the proof of theorem 1.7.5 last semester, so I'm not going to write down the proof again. It's exactly the same, you just change some absolute values to some distances. It just says that f is continuous at A, where f is still a function from x to z, x and z are still metric spaces, A is a point in X. I don't feel like writing it out. If and only if for all positive numbers epsilon, there exists a positive number delta such that if the distance from x to y, from A to x is less than delta, then the distance, now we're in z, so we have to use rho, from f of A to f of x is less than epsilon. Let's mention a couple of other results where the proof is either exactly the same as it was in section 1.7 or, very straightforward. So here's proposition 1.7.4, which turns into 5.4.4. So let's let xd and let's say y delta and z rho be metric spaces. A is a point in X, f is a function from X to Y, and g is a function from Y to Z. If f is continuous at A, and G is continuous at f of A, then the function f composed with G is continuous at A. This is a function, note, whose domain is X and whose range is Z. Here's another proposition. This is proposition 1.7.2 or 5.4.5. So we're going to let XD be a metric space. And A be a point in X. And then the idea is that the sum of two continuous functions is still continuous. You just have to be mapping into the kind of space where adding things makes sense. So your domain has to be the real numbers, or maybe RP, but your range has to be RP, but your domain can be an arbitrary metric space. So if you've got two functions, f and g, that go from X to RP, and f and g are both continuous at A, then the function f plus g, where you would take any point in X, you take f of X, g of X, and add them together. And the inner product of f and g, that's, you take their dot product, that gives you a real number. Those are continuous at A. The version with the dot product isn't, of course, in section 1.7, because 1.7 is all about R, not RP, but the proof is pretty straightforward. And then if you're in a space where you can multiply, so I don't know how to multiply real numbers. Well, I can take the dot. I don't know how to multiply vectors in general. I mean, I've already talked about the dot product, but scalar multiplication, that also preserves continuity. If you've got a continuous function into RP, a continuous function into R, then so is the function g times f. And you can also do division. I'll write this as if g is a function from X to R, g of A is not equal to 0, and g is continuous at A, then 1 over g is also continuous at A. And then you can combine this with part B if you want to get f over g being continuous. And then there are two propositions from section 4.1 and that are very much like the propositions from section 1.7 we talked about above, in that the proof in the general metric space setting is exactly the same as the proof in the real number setting. You just replace your absolute values by your distances. So I'm not going to go through the proof again. So let's let Fn, Gn, Hn be three sequences of functions and f be a function from x to z. We'll use the same xd. 0 is a metric space set up as in the definition. And then we've got the squeeze theorem for uniform convergence. If your Gn is between your Hn and Fn for all natural numbers n and all points in your domain, and if we've got that the top and the bottom both converge uniformly to f, then your middle function is also going to converge uniformly to f. There's a very important theorem from section 4.1 that generalizes to metric spaces in a very straightforward fashion. So let's suppose that Fn converges uniformly to f, where Fn and f, the setup is the same as in the definition. They're functions from x to z, where xd and 0 are metric spaces. Then if each of the inputs are continuous, where continuity now is as in definition 5.4.1 or proposition 5.4.2. And then the conclusion is that the target function, the thing you're converging to uniformly, is also continuous. And you can use these generalizations anytime you want to. There are also a couple of definitions and propositions from section 4.1 which generalize to metric spaces perfectly. So we're going to start by generalizing the definition of uniform convergence. So we start with two metric spaces. And then we're going to take a function f and a sequence of functions fn that go from x, whose domain is x, and whose range is z. Then we say that fn converges to f uniformly if for every positive number epsilon, there is a natural number n such that if little n is bigger than big N, then the distance in z, and therefore rho of f of x, the distance from f of x to fn of x, is less than epsilon for all x in the set X. I suppose that technically we don't need XD to be a metric space. If X was just a plain old set, you can still define uniform convergence, but we're going to be working just in metric spaces, so we'll define uniform convergence for metric spaces. We can also write down the definition of uniform continuity. That's another thing that's exactly the same as it is in the case of the real numbers. So let's we're going to start with two metric spaces. And a function from one to the other. And we're going to suppose that for all epsilon greater than 0, there exists a delta greater than 0 such that if x and y are in X and the distance in X from X to Y is less than delta, then the distance in Z, meaning we have to take rho from f of X to f of Y, if that's less than epsilon. So if that's true, then we say f is uniformly continuous. So we've seen there are a lot of results for continuous functions defined on subsets of the real numbers that actually work for continuous functions defined on arbitrary metric spaces. But there are some results that do not. Mostly these are results that require a little bit of extra structure. For example, the extreme value theorem, this is theorem 1.7.6. This only works in closed bounded subsets of the real numbers. And so the generalization doesn't work in arbitrary metric spaces because it doesn't work for all real numbers. And theorem 1.7.16, which says that all continuous functions on a closed bounded set of real numbers are uniformly continuous. It's the same way. So to generalize these guys, we're going to need a little bit of extra structure to our metric spaces, and we'll see how that works in section 5.5. So the extreme value theorem in general compact metric spaces is going to be corollary 5.5.3, and the proof that continuous functions are uniformly continuous in compact metric spaces, that is going to be theorem 5.5.10. And similarly, the intermediate value theorem, that only works in intervals, which are very special in a different way. So the intermediate value theorem will be able to generalize to general connected metric spaces in section 5.6. So the intermediate value theorem is going to be corollary 5.6.5. And proposition 2.3.9 that says that any continuous bijection has a continuous inverse. We will be able to write down a generalization of that. We'll use propositions 5.5.2 and theorem 5.4.3, and I will write down a full generalization of this when we get to section 5.5. So now I'm going to state theorem 5.4.3. This is sort of a new way of thinking about continuous functions. This is a sort of very abstract way of thinking about continuous functions, but it's going to be very useful to us going forth. So we take a function between two metric spaces, and then the following statements are equivalent. So the first option is that f is continuous at A for every point in our space X. The second object is that if U is an open subset of our target metric space, then F inverse of U, let me remind you what that is. That's the set of all X in X such that F of X is in U is open in the metric space it lives in XD. And the third equivalent condition of part C is that if D is a closed subset of Z, then it's exactly like option B with open and closed. Then F inverse of D, I think I will not write out the definition of that, is closed in the metric space XD. Let's start by proving that B and C are in fact equivalent. So first off, let's suppose that E is a subset of Z. And then if X is in if X is in X, then either F of X, F has domain X, so F of X is defined for all X is in X, so F of X is somewhere in Z, so either it's in E or F of X is not in E. That means it's in the complement, it's in Z minus E because it has to be somewhere in E. So we can always write X this way. We can write it as F inverse of E, that's the set of all points that get mapped into E, disjoint union F inverse of Z minus E. And the U with a bracket means X is the union and also they are disjoint from each other. So every point in X is in exactly one of them. You cannot have F of X being in both E and the complement of E. So put this another way. The complement of F inverse of E is F inverse of the complement of E. Complements taking in whatever space they have to be in. So now we're going to suppose B is true. And we're going to show that C is true. Let's let D be a closed subset of Z. Then we remember by definition 5.3.1 that Z minus D is open. So by B, F inverse of Z minus D is open. And the complement of an open set is closed. So we've got that X minus F inverse of Z minus D, which the complement of F inverse is F inverse of the complement F inverse of Z minus D, which is just F inverse of D, is closed. And that's exactly how C holds. And you do the exact same argument with the letter D switched for U and the words closed and open switched with each other. So I'm just going to write similarly. If C holds, then B holds. So C and B are equivalent to each other. Now I'm going to use the little ball characterization of an open set and the epsilon delta definition of continuity to show that A and B are equivalent to each other. You can also do this. You can also show that A and C are equivalent to each other. You can use the sequence characterization of closed sets and also the sequence characterization of continuity. And I'm not going to do that in this video because if you know that A and B are the same and you know that B and C are the same, then you know that A and C are the same. But however, the closed set with sequences argument is quite likely to show up as a homework or exam problem. So now let's suppose A is true. So we're assuming that our function f is continuous. And let's let U be an open subset of Z. And this is a very long and complicated argument, so let's draw in some pictures. Here is X. Here is Z. And then here is our region U. And then F inverse of U is over here somewhere. Our goal is to show that F inverse of U is open. So what we're going to do is we're going to pick a point X in F inverse of U. And we're trying to show that F inverse of U is open, so we're trying to show that around this little point X, we can draw a little ball that's in F inverse of U. But then F of X is in U somewhere. So here is F of X. F of X is in U by definition of the set F inverse of U. And then U is open. So by proposition 5.3.3, there is a Proposition 5.3.3 calls this number R, but for nefarious reasons of my own, I'm going to call it epsilon, a positive epsilon, such that the ball centered at f of x of radius epsilon is contained in U. Then by our epsilon delta characterization of continuity by proposition 5.4.2, there is a positive number delta such that if y is in x and the distance from x to y is less than delta, then the distance from f of x to f of y is less than epsilon. But let's rewrite that. If y is in x, if y is in x and the distance from x to y is less than delta, that's exactly the same thing as if y is in the ball centered at x of radius delta. Sorry, this distance needs to be a rho because it's a distance in z. And then if the distance from f of x to f of y is less than epsilon, that's exactly the same thing as f of y being in the ball centered at f of x of radius epsilon, which we remember is a subset of u. So the point is our epsilon delta characterization of continuity means that there is some little ball centered at x whose radius is delta, such that the image of that is contained entirely in this ball centered at f of x of radius epsilon. It might not be equal to the ball, it might be some sort of strange blobby thing, but it's contained entirely in this ball, which means it is contained entirely in u. So what that means is that, so if y is in the ball centered at x of radius delta, then f of y is in u, so y is in f inverse of u. So what we've seen is that for every point x in f inverse of u, then there's a ball centered at x of radius delta contained in f inverse of u for some delta greater than 0. So so that means that f inverse of u is open. So we've seen that if A is true, then B is true. And we've seen that B is equivalent to C, so we just need to show that B implies A. And we can reverse this argument to show that B implies A. So we're going to suppose that B is true. And then we're trying to show that the epsilon delta characterization of continuity works. Let's let x be a point in our domain and epsilon greater than 0. Then what is it we want to show? We want to show there's a delta such that if y minus x, y is within delta units of x, then f of y is within epsilon units of f of x. So, and we just saw that being within epsilon units means you're in the ball centered at x of radius epsilon. So let's let u be the ball centered at f of x of radius epsilon. That's a subset of z is open. So by B, by assumption B that we're assuming, f inverse of this ball is open. All right, and now x is an element of this open set. F of x is clearly in the ball with center f of x and any positive radius. So by our proposition 5.3.3, there is a positive number delta such that the ball centered at x of radius delta is contained in F inverse of the ball centered at f of x of radius epsilon. And let's translate this thing I've just said into distance land. So if y is in x and the distance from x to y is less than delta, then y is in this ball centered at x of radius delta, which is contained in F inverse of this mess. So that means that just by definition of F inverse, we've got that f of y is in the ball centered at f of x of radius epsilon. So that means the distance in z from f of x to f of y is less than epsilon. And that's exactly the epsilon delta characterization of continuity. So by proposition 5.4.2, F is continuous at the point x. And since we've done this for all x, since x was arbitrary, this holds for all x. So A holds, so we've seen that B indeed implies A. And that completes the proof.